Thanks for joining me in this lecture. This lecture will cover what's in the course. Welcome to Applied Machine Learning with BigQuery on Google's cloud platform. Let's talk about what's in the course. BigQuery is Google's serverless, highly scalable, enterprise data warehouse. Before BigQuery became a cloud service, it was used internally at Google millions of times a day. Before it was BigQuery, it was called Dremel. Dremel was a query-like service that allows you to run SQL-like queries against very large datasets and get accurate results in mere seconds. You just need a basic knowledge of SQL to query extremely large datasets in an ad hoc manner. At Google, engineers and non-engineers alike, including analysts, tech support staff, and technical account managers, use the technology thousands of times a day. BigQuery is the public implementation of Dremel. In this course, you'll learn how to use BigQuery to massage and navigate datasets at scale. BigQuery has many use cases, and this course will focus on how to get the most out of BigQuery as a machine learning engineer. Most applied machine learning is supervised. That means machine learning models are built against existing datasets. In the applied space, these datasets can be massive. Most organizations simply don't have the hardware resources to build their models against a dataset with a billion rows or more. For comparison, BigQuery can return 35 billion rows in 10 seconds. BigQuery provides machine learning engineers a location to house their datasets regardless of scale. If you want to build a model against a petabyte of data, BigQuery can handle it. BigQuery uses a different approach to return data to the end user. BigQuery stores data in columnar storage, which means it separates a record into column values and stores each value in different storage volumes. Whereas traditional databases normally store the whole record on one volume. This technique is called columnar storage, and it's been used in traditional data warehouse solutions. In the course, you'll learn the advantages of columnar storage and dig deeper into BigQuery's architectural details. In the course, you'll learn how to use BigQuery based on real-world case studies. These case studies will walk you through the end-to-end process of working with BigQuery. You'll learn how real-world models are built from end to end. The phrase end-to-end simply means working through the sundry steps in the machine learning pipeline. You'll learn how to source data, clean the data, and finally model the data to create a highly predictive model. Throughout the course, the focus will be on how to leverage BigQuery to build your models. Thanks for joining me in this lecture. Google is a data-driven company. If you're trying to make a point or start a project and you have the data to back up your idea, there's a good chance your idea will be accepted. Big data is a fuzzy term, and that was done deliberately. For most of us, big data is just more data than you can handle using traditional tools like relational databases. Now, you can house a petabyte of data on commodity hardware. However, querying that data isn't going to be a lot of fun. At this level, the size of your data is a pain point, and this data would be considered big data. Regardless of the technical minutiae behind the definition, working with large data sets is challenging, and Google helped pioneer many of the approaches used today to combat those hurdles. Google has had two major periods of data enlightenment. The first period between 2000 and 2006. During that period, Google produced several technologies that built the foundation for big data. The second period, after 2006 to present, has been to enhance and polish the tools they originally created. The technologies created during these two periods continue to be used as a foundation for Google's data-driven approach. Machine learning is one of the most sought-after careers on the planet, and that's not just within the IT space, that's everywhere. I should add here that the single most sought-after job in the world is that of the data engineer. That statistic is from Google, it's not something I just fabricated. Machine learning lives under the AI umbrella. Almost all applied machine learning is data-driven. As an aside, the words applied machine learning simply mean real-world machine learning, not machine learning research or anything else at the collegiate level. Machine learning is simply finding patterns in the data we can use later to make predictions using fresh data. Fresh data is data the model has never seen before. Machine learning engineers need to be able to build their models against highly structured datasets, the very kind of datasets that BigQuery thrives at storing. Now, BigQuery is a Google Cloud product. In order to use it, you're going to have to interact with the Google Cloud Platform. Most professionals shorten the Google Cloud Platform to GCP for brevity. Going forward, I'll often refer to the Google Cloud Platform simply as GCP. In this section, you're going to set up a GCP account, so we can use it with BigQuery. Now, it's important to point out here the course will only focus on services specific to using BigQuery. GCP is very large, and our focus for the entirety of this course will only be on BigQuery. Thanks for joining me on this introduction to applied machine learning with BigQuery on Google's Cloud Platform. This lecture will introduce scaling for big data at Google. The more data you have, the more resources you'll need in order to work with that data in a timely manner. Now, I'm using the term resources here strictly from a hardware perspective: CPU, memory, and disk. There are two ways to scale out your hardware resources. The first way is up, and the second way is out. Scaling up means buying larger servers with more resources. Scaling out means using lots of hardware and spreading the load across many servers. Google initially rejected scaling up because of cost. Buying thousands of Tier 1 servers is expensive. The question became, wouldn't it be more cost-effective to purchase 50 smaller servers for the cost of that one big one and spread the load out across those 50 servers? The answer was yes. However, it does mean you'll have to design your applications for massive parallelization. Scaled-up servers provide no redundancy. If you spend $100,000 on one super server, you'll need a second one as a standby in case the first one fails. That's an incredible amount of money wasted on idle, expensive resources just sitting there waiting to be used. Additionally, vertically scaled boxes have hard limitations. You only have so many slots for CPU and memory. If your server runs out of memory or your CPU is penned, then it's time to buy another pair of servers. Once Google settled on scaling out, there was no turning back. They began building their entire data stack using the scale-out model. Thanks for joining me in this lecture. This lecture will introduce several of Google's guiding principles for scaling. Let's take a look at the evolution of the big data stack at Google. Between 2000 and 2004, Google began creating real-world approaches for managing their ever-expanding big data universe. Initially, Google wrote down some guiding principles. The first major principle was that anything could fail at any time, and that the software design had to account for that. At most companies, when a database server fails, it's a critical event. The same thing can be said about a switch dying. The second guiding principle has to do with hardware vendors. The term often used here is commodity hardware. Commodity hardware simply means computer that is affordable and easy to obtain. Using this approach, Google didn't get locked into any one vendor, and could easily switch vendors without incurring any penalties. If you're using Dell servers and they become too expensive, you simply switch to HP. Lastly, hardware is expensive. The guiding principle for all applications must be to scale out and not up. These principles inspired new architectures and cut costs significantly. Google designed three key technologies that moved them towards the scaled-out revolution. The first one was GFS. This is the Google File System. GFS was a distributed cluster-based file system. The data is stored in multiple locations and is still available regardless of disk failure. The second technology was MapReduce. MapReduce gained massive popularity due to its ability to split and process terabytes of data in parallel, achieving quicker results. MapReduce facilitates concurrent processing by splitting petabytes of data into smaller chunks, and then processing them in parallel on Hadoop commodity servers. In the end, it aggregates all the data from multiple servers to return a consolidated output back to the application. The next big technology was Bigtable. Bigtable uses structured storage and scales out to multiple servers. Bigtable data is also replicated. Therefore, a single or even multiple hardware failures doesn't cause data loss. Using these three technologies, Google replaced most of their off-the-shelf software used to run their business. This was the Google Data Stack 1.0. Over the coming years, Google built their organization on top of these technologies and moved in the direction of their initial tenet: scale it out. Colossus replaced GFS. GFS didn't scale very well, and its fault-tolerant had a lot to be desired. Now, much of the architectural details of Colossus are not publicly disclosed. However, it is the underlying disk subsystem on which much of Google is built. For example, BigQuery relies on Colossus. Each Google data center has its own Colossus cluster, and each Colossus cluster has enough disks to give every BigQuery user thousands of dedicated disks at one time. Colossus also handles replication, recovery, and distributed management, so there's no single point of failure. Colossus is fast enough to allow BigQuery to provide similar performance to many in-memory databases, but leveraging much cheaper yet highly parallelized, scalable, durable, and performant infrastructure. The second technology for DataStack 2.0 was Megastore, a highly distributed NoSQL type data store. When data is written to one data center, It's also immediately replicated to another geographically dispersed one. Lastly, there's Spanner. Spanner is Google's scalable, geographically distributed, and synchronous replicated database. Again, it uses Colossus to distribute data at a global scale and support externally consistent distributed transactions. Although Spanner is relational and designed to be for OLTP, it can also handle in-database operational analytics. The new stack was built to address many of the problems that version 1.0 suffered from. While the Big Data Stack 2.0 still has some rough edges, no other company on the planet allows you to move big data around at the same speed you move smaller datasets around. Thanks for joining me in this lecture. In order to use Google Cloud Services, you'll need an account on GCP. Let's start by navigating to a browser. We could type out the entire name, but Google understands the GCP acronym, which means all we have to do is type 3 letters, GCP. Once the search is completed, GCP is our first result. Let's click on that result. You're taken to the GCP signup screen. Click on the Try Free button. Google recognizes one of my accounts and suggests I use it. I decline because I've created a new account for this course. You must have a Gmail account to use GCP. Once I type in the account I'd like to use and my password, the account on GCP is ready to go. Now, you might be tempted to gloss over the information on the right-hand side, but it's important. You're given a $300 credit to use on GCP, and the auto charge feature won't kick in without your confirmation. Okay, let's agree to the terms and continue. On the next screen, Google wants some information about where you live. Most of my information autofills. The last piece of information you'll need is a credit card. Once you've given Google a valid credit card, you're passed to the welcoming screen. Congratulations, you're ready to navigate the entire GCP landscape. More important, you're ready to use BigQuery. The screen you're viewing now is a GCP home screen. All right, the next thing I want to show you is billing, because no matter where I've worked, everyone's wanted to know what their bill was going to be. And more importantly, they've wanted updates along the way. So let's go find out how to do that. We come over here to the navigation menu, we click on it. So here is our overview of our billing account. Now, we really only have 2 sections here. We have the credits, which we've talked about a little earlier. You're given $300 of credits when you sign up, and it lasts a year. And it's letting me know I also have 340 days remaining. So we have projects linked to this billing account. Now, in a second, I'm going to show you how to set up an alert. However, it's important to understand that alerts are just that. They're alerts sent to the billing account email that let you know you're billing along the way. They're not going to shut down the account once you reach your maximum. However, if you'd like to disable billing because you've hit a limit, you can come here to any of your projects and let's disable for a cloud. So we'll click on that little ellipsis and we'll hit disable billing. And we're going to get a little message here that says, hey, when you disable billing on this project, it's going to shut down all the services associated with this project. So just as long as you know that, you can go ahead and disable billing and you won't be charged anymore on that project. I want to cancel out of that. And I want to navigate to budgets and alerts. So let's click on budgets and alerts. We're going to create a budget. And to do that, we simply click on create budget. In the budget, we need to give our budget a name. We'll call this Mike's, can't type, budget. And on our next drop down, it's saying what account do you want associated with it. It can be the entire billing account, or it can be an individual project. All right. I want to do it on the entire billing account. Next, we want to specify the amount. So let's put in $1,000. And when I type $1,000, you will see the budget alerts that are created down here. Now, you can add and alter these, but 50 and 90 and 100% are good budget alerts. All right. So here we have this cost after credit. And if you click on that, it says this is a cost after credit for the total minus any applicable credit. So if you want that, you simply click on that. Either way, whether you click on that or not, I really encourage you to set up billing alerts, even if it's just your account. Let's go ahead and save. And now we've set up a budget that will send the billing administrator an email once those targets are hit, the 50, 90, and 100% targets of the specified amount. To delete it, pretty straightforward. You click there. Up here, we have delete, and we will be able to delete that budget. So let's go ahead and delete that budget. And now we have no budgets. All right, we've gone over the basics of billing, and we set up a simple alert to alert us when specific targets are hit. Thanks for joining me in this lecture. In this lecture, let's discuss what will be covered in this section. By 2012, there were 100 billion searches done every month on Google. Trying to keep up with that amount of data was a laborious task. Initially, Google spent a lot of money on hardware for relational databases, yet it was still hard to get any real-time analysis on their data. In this section, you'll find out why this led to the creation of BigQuery. If your data doesn't live in BigQuery, you can't query it. BigQuery only stores and operates on structured datasets. A table in a relational database is an example of an object with fixed schema. When a table is created, you define what gets stored in that structure. In this section, the cloud storage system will be covered. Recall that Google's infrastructure decision was to scale out and not up. When you run a query on BigQuery, your query is likely to be run on massive clusters. The number of processor cores on these clusters is likely to be in the thousands, and the number of disks in the hundreds of thousands. This section will cover parallel execution of your BigQuery queries. Most of the interaction you'll have with BigQuery in this course will be via the cloud interface. With the UI, you'll be able to create and execute queries, create tables, share datasets, and export your data. In this section, the basics of navigation via the web interface will be covered. BigQuery isn't an isolated tool at Google. BigQuery is built on top of other technologies like Bigtable and Colossus. This section will uncover some of the architectural details behind BigQuery. For example, BigQuery metadata is stored in Megastore. However, the actual data is stored on Colossus. The section will also cover the foundation of BigQuery navigation. You'll complete several demonstrations using the web UI. Sections will build on one another, so I'd highly recommend you move through the course in a serial fashion. Thanks for joining me in this lecture. In this lecture, let's define what BigQuery is. Google's exponential data growth was causing problems. Google needed a tool that enabled interactive queries over big data. Yes, Google invented MapReduce. However, MapReduce is a batch-oriented technology. Getting answers from MapReduce jobs takes a long time. Google needed something more interactive. BigQuery is a tool used to enable interactive queries over datasets at scale. The term is scale invariant. That simply means that BigQuery should operate the same way whether you're querying 50 rows or 50 billion rows. Now, obviously, there's going to be some time difference between the 50-row table and the 50 billion row table. However, the 50 billion row table in BigQuery still returns results to you in minutes. Google's need for a tool that enabled interactive query analytics over large datasets led to the creation of Dremel, which gave Google employees the ability to run queries over very large datasets. The popularity of Dremel at Google persuaded Google to provide the service to their customers. That service is called BigQuery. The default language in the world of relational databases is SQL. One of the great things about SQL is its ubiquity within the organization. At most companies, it's quite common for people outside of IT to be familiar with SQL and use it to ask questions of their data. Even though BigQuery uses a non-standard dialect, it's still SQL. That means the learning curve for anyone who knows SQL will be short. Most relational databases can take advantage of parallelism. However, they often parallelize the queries across multiple processors, rather than taking advantage of multiple processors for a single query. The Dremel engine parallelizes SQL execution across thousands of machines. With Dremel, if you want your queries to run faster, you simply throw more computers at it. At Google, one of Dremel's performance goals was to return a terabyte of data in a second. They've accomplished that and more. If you've worked in the world of relational databases at all, you'll know that kind of speed is insane. Thanks for joining me in this lecture.